So in this video, we are going to expand on the concept of dispersion, which is when different frequencies propagate at different velocities or different speeds. And we'll also talk about the physical nature of where attenuation comes from. So let me just start by taking you back to the example problem that we did in the previous video, in which we had an audio cable. We looked at the data sheet. We wrote down the 4 key transmission line parameters: the inductance per unit length, the capacitance per unit length, the resistance per unit length, and the admittance per unit length, although the fourth one was 0. We figured out the full propagation constant called gamma and plugged it into this equation over here. And assuming that the frequency was 20 kilohertz, which is about the high end of what an audio signal might have. And this is the value of gamma that we came up with. The real part of it defined the attenuation, and the imaginary part defined the propagation, or how the phase evolves with time. And so from that, we figured out that we would get approximately 6.3 kilowatts of energy reaching this far speaker about 1 kilometer away. All right. Now, one thing that I said in that video, which is true, is that if the frequency changes, so too will gamma, and so too will the ratio of alpha to beta. The relative effects of propagation and attenuation are going to change as a function of frequency. And that's a notion called dispersion. And so let me show you now, if we were to redo these calculations at many different frequencies, this is what we would plot for alpha and for beta. All right, so the left plot is beta as a function of frequency. And we did the calculation at 20 kilohertz, but this is beta here. And so remember that beta equals omega divided by the propagation velocity, right? Or it's 2 pi over the wavelength. Those are the same. So we would expect in a lossless and ideal case that beta is proportional to the frequency, right? So there ought to be a straight line to it, which you can sort of see for most of this curve. This line here is pretty straight, right? There's no question that's a straight line. But down here at the lowest frequencies, that is no longer the case. So this would imply that the propagation velocity Vp is changing as a function of frequency when you get down to the lowest frequencies of, let's say, below 1 kilohertz into the 100 hertz range. Right, so that's something we're going to talk about. On the right is this attenuation, or alpha, in units of meters per meter. So this is how many 1/e reductions are we seeing every meter. And that starts out with a value that technically at DC it's 0, and then it slowly increases with this sort of fashion. At 20 kilohertz, it had reached a point where the 10 kilowatt signal drops to 6.3 kilowatts, but you can see the trend is clearly increasing with frequency. And as the frequency goes up, it will increase even further. So at a certain point, this attenuation would get too high if you increase your frequency. So this cable is optimized for the audio, but I would not advise ever using this for let's say a gigahertz signal. Clearly, this cable would not work. By the time this attenuation gets out to 1 gigahertz, it would be way too high for this cable to be useful. But it clearly works pretty well in this scenario. So let's talk about this, because this lower portion right here, this dispersive section, where the propagation velocity appears to be a function of frequency, let's talk about where that comes from. In this case, the propagation velocity is basically the slope of this line. So let's take a closer look at that. All right, so for the low loss case, we had that alpha equals R over Z0 plus Z0 times G over 2. And we had that beta equals omega over Vp, the propagation velocity. All right, that's for the low loss case. In reality, though, this Vp is not a constant. It's a function of frequency. And so if we sort of take a look at this more generally, what we'll find is that there is a certain condition that causes VP to be pretty exact. And that condition is for R over L to equal G over C. If that condition is met, that would imply no dispersion, right? Or no variation in VP as a function of frequency. If VP is a function of frequency, this is what we can expect. This is a concept of dispersion. Let's say we have a pulse like this. All right. I'm going to draw a Gaussian pulse. This Gaussian pulse consists of lots of different frequencies, varying from DC up to, depending on the size of this Gaussian. It could be tens of kilohertz or megahertz or gigahertz, or whatever it is. But the mix of frequencies that make up this Gaussian wave are each traveling at different speeds. And so after this disperses, what you would see is something that looks like this. It would probably be kind of bouncy over here, and then it might, it might be a little bouncy over here. It'll kind of rise and be bouncy again over there. So this is a little bit of dispersion affecting the characteristic of the signal. So oftentimes in these design of very, I guess, critical cables, like ones that are linking very high frequency signals, you try very hard to design the transmission line for this condition to be met in order to reduce dispersion. The trouble here is that, as we mentioned, G is very often 0, right? And so if R is non-zero, because you can't avoid R being non-zero, right? There will be some non-zero, resistance value to the long transmission line. And so if R is going to be non-zero, the only way for this condition to be met is for G to be non-zero. So that implies, ironically, that you might want to intentionally fill your transmission line with a material that has just a little bit of loss or a little bit of conductivity to it in order to try to make this condition work. The downside is you'll create a little bit extra attenuation, and so you'll kill your signal strength a little bit slowly as a function of length. But the flip side is you may be able to decrease your dispersion, and that is very important. If we're sending a digital pulse, for example, right, going back to the digital case, right, where we send this little digital pulse, and this digital pulse, again, consists of lots of frequencies on up to maybe gigahertz, right? If this is a gigahertz pulse with a rise time of a few nanoseconds, we've got gigahertz in this signal, right? You can't generate this sharp rise without a gigahertz component. And what dispersion is going to do is it's going to make the signal look kind of like this, right? It's going to kind of rise a little bit slower and have a little bit of ripple on both sides. Because again, those different frequencies are slowly pulling apart, and that's damaging. And in the course of a digital application, if we have a sharp square wave like this, the worse our dispersion is, the more this square wave stops looking like a square wave. So the dispersion basically limits the speed that we can operate a digital signal. And for that reason, it's very helpful to ensure that we minimize dispersion in a lot of very high frequency and high speed applications. All right, I want to talk about a couple other things, which is how does lossy attenuation on transmission lines affect the input impedance? Right, we have this notion of a transmission line. And there's a load at the end. This transmission line has length D, and it has impedance of Z0. And if we want to talk about the apparent impedance viewed at the beginning of this transmission line with this load at the end, it worked out to be Zn equals Z0 times ZL plus tangent of beta D divided by Z0. Oh, I forgot the Z0 there. Z0 plus CL times tangent of beta D. All right. Now, in order to modify this for lossy transmission lines, it's actually a pretty simple modification. I'm going to get rid of this tangent, and I'm going to replace it with a hyperbolic tangent, right? Where the hyperbolic tangent is the following: tan h of x equals e to the 2x minus 1 divided by e to the 2x plus 1. This is a definition of hyperbolic tangent. If you plug this in, then you can repeat the same techniques we used before to figure out the input impedance. Long story short, as the other modification we have to make, by the way, is beta is only part of the story. So we're going to get rid of beta, and instead we're going to put gamma. All right. Long story short, if we have a lot of attenuation, what's going to happen is that we're going to attenuate the signal. So if we consider V in, sorry, V, sorry, not V in, but Z in. If we consider Z in, sort of the original definition was it's the input voltage plus the output voltage divided by the input current plus the output current. What's going to happen if we add attenuation is that these two terms will shrink. Right? These shrink with high attenuation, because that's the leftover voltage and current after we propagate to the load, reflect, and propagate all the way back out. Right? So shrink with increasing attenuation. And so for very high attenuation transmission lines, we're going to expect Zn to just settle out to be Z0, because we've sort of killed the reflection. Nothing is coming back to the source. And in fact, that works out to be the case if you plug in a gamma that reflects high attenuation. Then these will be gone, and Zn will equal Z0. All right. One more comment about what we're going to have to change, which is technically the value of Z0 is going to have to change as well. All right. Our original definition of Z0 was square root of L over C. For the lossless case, to account for lossy propagation lines, we're going to replace this with the square root of R plus J omega L divided by G plus J omega C. So Z0 will also be a complex number. And all that really means is that for a propagating wave along this antenna, or sorry, along this transmission line, there will be a phase shift between the voltage and the current, right? And that's okay. And Z0 captures that because, again, this will give us a complex number that refers to a phasor multiplier, where V divided by I, both of these as phasors, will equal this value Z0. Right? And the angle of Z0 will be the phase shift between voltage and current. All right. Just to add a little more detail here, a positive phase of Z0 implies the voltage is ahead in phase. Right, so the current lags behind. All right. Now, the last thing I want to talk about is the physical source of this resistance per unit length and what actually determines it. So I'm going to draw this little diagram here of a coaxial cable. All right, here's the inner conductor shaded right there, and the outer conductor is all of this. So let's say that the coaxial cable is typically built out of copper, and copper has a conductivity sigma, where copper is 5.9 times 10 to the 7th. We're going to learn much more about this later. But the conductivity of copper is about this number. All right. Now, there's two factors that are going to be important. The first is called the skin effect. And so that is, if we zoom in right here on the surface of this conductor, what's going to happen is the current is all going to be confined to a little slab just beneath the surface. And this is called the skin effect. Right, so the current has to be squeezed inside this little tube on just below the surface, and the diameter or the thickness of that tube is given by something called the skin depth, and it's usually a lowercase delta, which equals the square root of 2 over omega mu sigma. Right? So what ends up happening is as we go up in frequency, the current is choked away into a thinner and thinner path, which means that effectively it's encountering a higher and higher resistance. So as the frequency goes up, typically we'll have more attenuation, right? Because the resistance per unit length is increasing as the frequency goes up. And there is another skin effect that takes place in the outer conductor, right? So the same effect is happening there. All right, so that's basically the origin of where resistance comes from. It tends to come from, even if you have a really high conductor, it comes from the fact that the current is squeezed only one skin depth or two inside of the conductor. And there's simply only a certain number of carriers there. And so that, by definition, means you have some resistance. All right, the admittance G is basically going to come from whatever material is filling the space in between the two conductors. And so whatever conductivity that material has, it's going to figure out what G is. A rough formula for G is for a coaxial conductor, it's 2 pi times omega times epsilon times the tangent of this skin depth right here, this lowercase delta, divided by the natural log of B over A, where B is the B is the outer diameter, or radius, whichever you prefer, and A is the inner diameter. All right, so that's sort of the physical nature of where this R and G comes from. All right, so that concludes this video and this section on transmission lines with AC signals. I hope you can now see that the analysis techniques are very different depending on whether you're talking about digital signals with sort of square wave, rapid falls and rapid rises, or whether we're talking about RF or analog or sinusoidal signals in which we're operating in a narrow frequency band. That narrow frequency band introduced a whole host of conditions that weren't the case for time domain signals. Now, these two are equivalent to each other. And what I mean is that you could take a time domain digital signal, convert it into the frequency domain with something like a Fourier transform or a Z transform, and then apply the single frequency analysis to each frequency, and then convert it back into the time domain. You would get the same answer if you did that. And so these two different approaches that we've talked about with the digital signals and the frequency based signal or the single frequency signals, they are two sides of the same coin, but it is the same coin. It's describing the exact same phenomenon of how waves propagate on transmission lines. So having concluded all this section right here, and we've come to understand the nature of how waves propagate, how they attenuate, how the phase evolves, the next thing we're going to do is we're going to set all that aside. And we want to come back to this later, but we want to dive into the details and really understand what's going on for real in these transmission lines. And these transmission lines are not voltage and current devices. They are really electric field and magnetic field devices. And we're going to eventually come to realize that the voltage and the current are simply consequences of those fields. And so the next section of the course, we're going to rebuild our understanding of electric fields and magnetic fields. And we eventually are going to come back and reconnect it and effectively rederive all of this, but simply with a electric and magnetic field understanding instead of voltages and currents. So I look forward to that. I think these will be some fun and interesting videos, but hopefully this section on transmission lines was enlightening and educational as well.